Hi folks, thanks so much for joining me today. In this video, we'll be exploring how to build a full-scale, commercial-grade laminar flow hood for mushroom cultivation and sterile culture work. This is a great DIY project you can tackle at home that will give you access to an incredibly powerful professional-grade tool at a fraction of the cost. First, I'll talk a little bit about what laminar flow hoods are, how they work, and why we use them. Then, we'll go over some design considerations, all the different parts, where to find them, and how to put them together. At the end, I'll conclude with some tips on how to use and how to maintain them. As always, I have a lot of details to cover, so feel free to skip ahead to the part you're interested in using the chapter markers. That said, this whole video is chock full of tips and tricks, so you might as well just sit back, relax, and enjoy. In short, a laminar flow hood is an extremely powerful, sterile air filtration device. Laminar flow systems are used in all kinds of different industries where a completely clean air environment is a necessity, from hospital operating rooms to electronics manufacturing to nuclear research laboratories. Of course, I assume that most of you are here for your interest in mushroom cultivation, or perhaps some kind of microbiology or sterile tissue culture for breeding plants. Whatever your interest, you've come to the right place. If you're new to mushroom cultivation, I encourage you to dip your toes in the water before you take the plunge. There are many great tools for getting started without having to invest in large or expensive equipment. You can get your cultivation journey off to a great start and help support the creation of these free educational videos by visiting my donation-based shop at fungaia.life, where you'll find a great selection of gourmet and medicinal liquid cultures, pre-sterilized grain spawn, all-in-one kits, and more. And make sure to go check out our partners and the sponsor of today's video, True Blue Genetics, at truebluegenetics.org, where you'll find an incredible selection of clean, vigorous liquid culture at affordable prices, especially when you show us some love and use the coupon code FUNGAIA to get 20% off and to let them know that we sent you. Now, if you've clicked on this video, chances are you're already aware that a laminar flow hood is the key to unlocking numerous doors in the fungal realm, particularly for sterile culture and breeding work. This is one of the major stumbling blocks for new growers and one of the biggest obstacles separating hobbyists from pros. Industrial laminar flow systems can be massive, take up whole rooms, cost tens of thousands of dollars, and even basic hobby scale units are out of reach for many new growers. In this video, I'll be describing the process for building a full-size commercial scale flow hood. I'll be using this flow hood for my business, and I hope to rely on it for many years to come. So I'm going to go the extra mile to get all new equipment and make something especially robust. So this project isn't exactly going to be cheap, but throughout the process I'll be offering lots of tips for the budget conscious. As with many such DIY projects, the trade-off is often time over money. So if you don't mind putting in a little extra elbow grease, I'll help you figure out how to build one of these for just a couple $100. That said, there are cheaper options out there, so I want to take a little bit of time to talk about those first. For one thing, as you see here, I've developed a desktop flow hood design that's extremely compact, that's meant to be an ideal choice for hobbyists, newcomers, and people who don't want something that's going to take up a whole room in their house. Unfortunately, it's turned out that I can't personally produce these cost effectively enough to make them as affordable as I'd like. I'd much rather be here making these videos. So instead, I've been working on a do-it-yourself kit that'll allow you to buy the parts and then assemble them yourself, and I'm making a video on how to put that together. I also developed a battery-powered version, which I'll show you how to make yourself if you're interested, that opens up whole new possibilities in field work and allows you to take your laminar flow hood on the go. So don't forget to subscribe so you don't miss out on any of those exciting developments. I've noticed some companies who are starting to sell cheap filter units as flow hoods that are actually just computer fans in conjunction with residential air filters. These are not true laminar flow hoods, and they won't perform at the standards required by most commercial operations. That said, they might work well enough for a dabbler to be worthwhile, but Don't be fooled into spending hundreds of dollars on something that's cobbled together out of $20 worth of parts. You'd be better off just building one of those yourself. The other flow hood alternatives that have been gaining popularity are fan filter units, or FFUs. These are often misleadingly referred to as flow hoods, but don't actually generate true laminar flow. Nonetheless, I know a lot of hobby growers are using them with perfectly adequate results. So this might be a good middle ground option for you if you're not quite ready to shell out for the real deal. On the plus side, they're compact and they're affordable. The downsides are that they're simply not as effective. They're also noisy, they're not very serviceable, and they tend to have a shorter overall lifespan. FFUs are actually made for things like downdraft ceilings and clean rooms, so they're really regarded as a consumable and they're meant to be periodically replaced. In general, with this kind of stuff, I find that you really get what you pay for. Filters in particular are not all made equal, so regardless of what you get, just make sure you take the time and you know what you're buying. If you're serious about mushroom cultivation and you know that this is something you want to pursue for years to come, then I think it's worth setting yourself up right from the start and investing in a powerful, beautiful tool that's going to last you a lifetime. Whatever direction you decide to go, I hope that this video will offer some helpful insights to set you up for success. Up next, let's turn to Professor Sporadicus for some helpful background info. Now, before we get all scientific, let's just start by taking a deep breath. Chances are, we just inhaled a couple dozen spores. On average, there are thousands of fungal spores in every cubic meter of air. Pretty wild, huh? That's why we use this special air filtration device called a laminar flow hood. Now, it's worth mentioning really quick that sometimes folks confuse the terms flow hood and fume hood. A flow hood pushes sterile air towards the operator to protect the work from pathogens, whereas a fume hood captures and exhausts the fumes to protect the operator from the work. Incidentally, there's another device that actually combines these two called a total fume extraction biosafety cabinet. These are specifically used when working with biological pathogens like viruses and infectious diseases. Let's talk physics. In fluid dynamics, there are two different types of flow: laminar and turbulent. Turbulent flow is characterized by swirling, eddies, cross drafts, whereas laminar flow is characterized by parallel, even, uniform movement. A laminar flow hood creates a laminar flow of sterile air, such that anything which is placed in that flow will be protected from any biological matter. Here's an analogy. Think about a big multi-lane highway full of traffic. As long as all of the cars are moving in the same direction in parallel lines, it would be extremely difficult to drive in the opposite direction. Now instead, think about a large roundabout. All that circular motion means that you could enter the circle at any point and reach any other point without ever going against the flow of the other cars. The same is true for fungal spores. As long as the flow is laminar, there's no way for those spores to move upstream. Remember, however, that just because we placed something in laminar flow doesn't somehow magically make it sterile. Not only do we need to adequately sterilize it first, but we also have to use specific sterile techniques to move and interact with it. Otherwise, all these precautions are totally pointless. For a much more detailed account of these sterile techniques, check out the other videos on how to use a pressure cooker and Mycology Lab 101. For now, I want to stick with talking about one more concept in fluid dynamics. An object which is immersed in laminar flow will only come in contact with fluid from upstream, but that object will in many cases create turbulence downstream. This is due to something called the Venturi effect. The air must compress slightly as it passes around the object, and then decompress again on the other side. This pressure differential usually causes turbulence, and in some cases, some of that turbulent air will actually move backwards upwind toward the object. This phenomenon is called a slipstream, and it can cause some problems in sterile culture work. To use another automotive analogy, this is very similar to what happens when you pass a large truck on the highway. Not only is the Venturi effect something to understand and track as we're using a laminar flow hood, it's also an important thing to consider in its design. The motion of the air as it exits the flow hood also creates a pressure differential and hence some Venturi turbulence at the edges of the workspace. This is why almost all professional laminar flow systems have a tunnel of some kind to channel the air and maintain laminar flow through a much larger usable workspace. Many mushroom cultivators forgo this feature when designing flow hoods, presumably for a little more elbow room, but it's my firm conviction that this is an indispensable and absolutely necessary component of all effective laminar flow systems. Next, let's talk a little bit about how a laminar flow hood actually works. The principle is fairly simple. The filter media is a finely woven mesh that creates some resistance as air passes through it. In order to push a lot of air through that filter, we need to create some pressure in the space behind it. To create that pressure, we'll use a specialized blower. Then we'll build a sealed box where the only way for air to get in is through the blower and the only way for it to go out is through the filter. This box is called the plenum. The blower is usually mounted perpendicular to the direction of laminar flow so that rather than just blasting air through the filter, as it forces air down into the plenum, it's creating a large mass of turbulent, swirling air behind that HEPA filter. Since the tightly woven filter media is uniform, its resistance is also uniform, which means that the air gets pushed through with equal force across the whole surface area of that filter. This is what creates that true, even laminar flow that we're looking for. Okay, now that we have a grasp of the concepts, let's talk about a few considerations for design. I want to walk you through my previous flow hood builds and talk to you about some of the decisions that I made and some of the things I've changed along the way. One of the most important choices you have to make is the size of your flow hood. This is the first flow hood that I built, and as you can see, it's a 2-foot by 3-foot filter. I used this flow hood for everything for the first several years of running the business, and aside from a few times it feel a little bit cramped, I think it's actually a really nice size. It's big enough to do everything that you need to do, but it is smaller and therefore quite a bit cheaper to build than the sort of standard 2-foot by 4-foot flow hood most people are using. Part of the reason I went with this filter is because when I built this flow hood, cost was my primary limitation. So I built it using a salvaged blower that I got from an HVAC company, and I had to get a smaller filter so that it would be within the specifications for that blower. It was also advantageous to have something a little smaller because I could easily fit it through the very narrow opening of the skate ramp where I built my first laboratory. Smaller filters are much cheaper to ship, which is a big part of their overall cost, so in this case, going with the smaller filter was definitely worth it. I know a lot of hobbyists out there are using an even smaller 2-foot by 2-foot filter for their flow hood. These filters are easy to find, and I'd say that space is sufficient for most of the transfers and the kinds of work you would need to be doing in front of a flow hood. However, a lot of the time you're going to want to have jars, bags, and some other stuff cooling under one side of the flow hood while you're doing work on the other, so having a little bit more elbow room makes a really big difference in the long run. One really important design consideration is the space between the bottom of your filter and the top of your work surface. Generally, when you build a flow hood, this is going to end up being a full 1.5 inches. And when I first built this unit, what I did is I created a floating work surface, which I've seen a lot of other people do. The problem here was that, as I described with the Venturi effect, there was actually a little bit of a vortex right here, and it created a little bit of a backdraft that I was able to trace some of my contamination problems to. So ever since then, what I've done is I always raise up my work surface and get it within about 1/2 inch of the filter. However, another problem that's actually more common than you might realize is if you're working with jars that get cooked over and over again, they break sometimes. So if you set a jar of liquid culture here and it's cracked and you don't realize it, you go to pick it up and it just deluges sterile sugar water all over your work surface. If that gets back into your HEPA filter, it can completely compromise your flow hood. So I always make sure to leave a little drip edge, and that way any liquid that does spill out is just going to run down the front. As you'll notice with all my flow hoods, and as I've discussed already, I always like to build a glass tunnel around the filter. So in this case, I just used some cheap glass that I got at the hardware store. I cut it myself using one of those little scoring tools, and it's just held in place with some glazing points and silicone. Pretty cheap, anyone could do it this way. However, it is really pretty shallow. I wish I'd made it deeper. And I did notice that with the wood in this orientation, it did create some turbulence around the edges of my laminar flow space. You'll also notice that I use glass on my work surface, and this is actually a piece of tempered glass that I got at a resupply store. I just happened to get lucky and find a piece that was absolutely perfect. I totally have fallen in love with this They're heat resistant, chemical resistant, they're extremely easy to clean. I think it looks nice. I really enjoy working with the tempered glass. So for all of my other flow hood builds, I've started getting custom glass cut. Just for this one piece for the work surface, you're only looking at about 60 or 70 bucks, and it's absolutely worth every penny. Now you can see here how when I originally built this flow hood, I used a variable speed controller. This is a router speed controller. It's basically the same thing as a light switch dimmer. After doing some more research, I realized this was actually a mistake. The problem is that these variable speed controllers will actually put a lot of undue wear on your motor. So what I'm going to advocate instead, and I'll show you how to do this in the blower section a little later, is putting in a cam switch. And in this case, I just bypassed the speed controller since it was already glued into place. This is the second flow hood that I built. And at the time, I really just wanted something that I could use for substrate, for cooling large batches of liquid media, and other kind of messier parts of the process. For this one, I made the tunnel much deeper, and I also used some dowels which I routed on a table saw to hold the glass in place with a little bit less resistance and turbulence on the edges. For this one, I also opted to just weld together a steel cart to permanently mount it to. The whole thing's on wheels, which is obviously very convenient, and I built this work surface with that filter gap in mind. So the work surface is raised up a little over an inch here. And then this is just bolted on so that I could take it off and wheel it through a doorway. One thing I definitely want to talk about here is most people will build their flow hood with the blower on top. Now, I made this for my old lab, which had an extremely low ceiling. It was basically just a closet. So I didn't have that option. I had to put it on the bottom. But what I found is that it actually was much more effective at cleaning the air in the entire room. If you think about a particle load in a room, there's always going to be more dust and stuff settled kind of at the bottom, in the bottom few inches of the floor. The conventional wisdom is that you put the blower on top and that's pulling in the cleaner air from the upper parts of the room to push through your filter. However, I basically want my lab to be a total clean room, so I want to be able to turn over the air in the whole room with my flow hood, and pulling from the bottom is actually helping do that more effectively. The other unanticipated benefit is that it creates a very considerable downdraft in the room, which means that any particles which are caught up in the air get sucked towards the floor rather than kind of having them held in suspension and a little bit more likely to float around. So when I moved into my new facility and built this flow hood, I decided to opt again for mounting the blowers underneath. And I have to say, the air cycling downdraft benefits are undeniable. It works really, really well, and it's able to turn over the air in the entire room very, very effectively and very quickly. I was tired of being cramped, and I knew that this is the single most important investment for my business, so I pulled out all the stops. I sprung for the full 2 foot by 4 foot filters to build this side-by-side unit, which I now use for most of my day-to-day lab work. This time, I built the tunnel a full 20 inches deep with a 24-inch work surface, and I built the entire thing out of 1/4-inch custom-cut tempered glass. I installed the work surface just below the filter, and I used just some flooring transition molding to hold the glass in place so that there's very little impact on the laminar flow. Another thing I want to point out that I don't talk about much, but this is actually very, very important. I use pre-filters on all of my flow hoods. Using a good pre-filter and replacing it often is the #1 way to extend the life of your HEPA filter. At about 16 bucks a pair, you can afford to replace these quite a few more times than your big expensive HEPA filter. In this video, I'll be documenting the construction of this flow hood for my new substrate and grain processing facility. Now, unlike the lab, which is a total clean room, this room is going to be dirty. It's going to have raw substrate materials brought in, and so I opted to put the blowers on top to prioritize preserving the life of my HEPA filters rather than trying to really keep the air in the room clean. As you'll see shortly, this is actually really just 2 separate flow hoods that share a piece in the middle. So the design is pretty much the same if you're building a single wide version. Now, I'll go over this in a lot more detail, but first I just kind of wanted to illustrate a few points in a very general way to help point you in the right direction, and hopefully these examples will help you decide what flow hood is right for your budget, for the space that you have, and for your fungal ambitions. I'll also leave you a link in the description to download a free PDF that'll show you a few different design ideas with dimensions and more specifics to help you get started. And now, let's move on and start talking about our components. Okay, let's talk components. In its essence, a flow hood is very simple. It requires a HEPA filter, a powerful fan, and then a box to hold them. Let's go over them in that order. As you've probably guessed by now, the real crux of a laminar flow hood is the HEPA filter. HEPA stands for high efficiency particulate arrest, which means that the filter media is actually trapping particles as they pass through. Now, there is no such thing as an absolutely perfect air filter, so we rate them by degrees. The efficiency rating of a filter is just the percentage of the particles of a given size that it can trap. For the vast majority of microbiology applications, the preferred efficiency is about 99.995% or higher at 0.3 microns, which is less than 1/3 of a millionth of a meter. For reference, that's smaller than about 1/100th the width of a human hair, and it's smaller than almost all bacteria or fungal spores. Now, many of the residential grade air filters that are marketed as true HEPA are actually only rated to about 99% efficiency in maybe 5 microns, which is large enough and inefficient enough to actually allow quite a lot of biological matter to pass through. While this is fine for filtering dust particles out of the air in your house, and it may actually be better than nothing as far as sterile culture work goes, it simply will not allow us to achieve the standard of sterility that we would like to for commercial applications. On the other extreme, there are some incredibly specialized filters called HEPA filters, which are rated to as high as 99.999999% efficiency at 0.12 microns, about the highest I've ever heard of, that we would use for incredibly specialized nuclear physics laboratories, for example. So, obviously with filters, there's always a trade-off. Higher efficiency means they're more expensive for one thing, and it also means that that tighter filter media needs a more powerful blower to push the air through. If you're really on a tight budget and you just want to get something that's better than your still air box, go ahead and try one of those cheap air filters. However, if you're going to go through the trouble of building a flow hood, you might as well invest in the real deal. These days, cheap Chinese manufacturing has all but gobbled up the entire HEPA filter market. Especially since the pandemic, you can pick up a solid HEPA filter for a fraction of what it would have cost you 10 years ago. Not all HEPA filters are made equal though, and like I've said, in general, you kind of get what you pay for. Now, most people are using cheaper filters these days, and for the most part, they work just fine. Just be wary of chemical off-gassing, of poor quality control standards, and in particular, of false marketing. Another good middle ground option is to find really solid, high-quality filters used at online auctions. But while I'm usually all for saving a buck, this is one of those things that I would really say it's best not to skimp on. The HEPA filter is the foundation of all of your subsequent culture work, so you'll never be able to achieve better results than what it can produce. Short term, maybe it doesn't make much of a difference. But if you want a flow hood that you can have in service maintenance-free and maintain a genetics library for many, many years to come, then it's worth doubling down on filter quality. A properly used, top-of-the-line HEPA filter can last for 3 to 5 years of consistent use. Now, maybe I'm just a schmuck, but I'm personally partial to the HEPA Corporation. They've been an industry leader for decades, and honestly, they're old school. I don't think they've probably changed their manufacturing processes or their products in over 30 years. And that's because they just work. They're still making their filters, just like they always have been, by hand, right in California. They're a wholesale producer, so if you only want 1 or 2 filters, you'll probably need to go through one of their distributors. Now, I know I'll probably catch some flack in the comments for saying this, but a great distributor of these filters is Paul Stamit's company, Fungi Perfecti. I know, he's a union-busting snake oil salesman, but many of us in the industry owe him at least some credit. Plus, his company sells these filters at one of the best prices I've found for HEPA Corporation filters specifically. The filter is the first and most important thing to acquire and will determine all of the other components that you need. The next thing you've got to figure out is the blower. In order to achieve laminar flow, we need to generate a significant amount of pressure to push through that tight filter membrane. That means we need to use very specific types of fans. For what we want to generate true laminar flow, we're going to need a high pressure blower. The best kind of blower for this is called a centrifugal blower. And as you can see, the way this is engineered, it's a little bit like a snail shell. And what that allows it to do is gradually increase the pressure as the air moves around that housing and then push it into our plenum to pressurize that empty space behind the HEPA filter. The main place that you'll find these blowers is in the central air system in most American houses. That's because you need a significant amount of airflow at pressure to push air to all extremities of a house. These blowers utilize a specific type of AC motor called a permanent split capacitor motor. And it's called that because it's got a capacitor that's actually permanently wired in to offset the phase of the power going into the motor in order to generate the circular motion. These motors are very powerful, usually rated about 1/2 or 3/4 horsepower for the kind of application we'll be using, and they're also fairly expensive. These blowers are often referred to by the nickname of squirrel cage blowers, and I think that's just because it's got this kind of hamster wheel impeller on the inside. In the past, I've had great luck just hitting up my local HVAC company. They're usually very willing to give me something out of their scrap pile. They usually replace and reinstall these motors and blowers all the time, so they have tons lying around. However, they often come out of houses where they've been in use for several years, so it's a good idea if you're gonna go that route to take the time to really clean it super well, disassemble the whole thing, maybe repaint it. Sometimes you need to replace the capacitor. It's about a $5 part, they're very cheap. Sometimes you might need to mix and match motors, so you've got to be careful that you're getting one that's about the right specifications for the application. Also, usually when I've gone this route, I've ended up just replacing the motor because they're very difficult to clean and they have a certain limited lifespan. So you can save yourself about $300 by salvaging the blower housing, which obviously can't really break. I mean, the bearings are in the motor, there's no actual moving parts in this piece. The motors themselves, you can usually get a replacement for about 150 bucks. So this being the second most expensive part of your build after the HEPA filter, it's a great way to save some money on your flow hood construction. As I'll explain here in just a moment, there are a few different ways to figure out what kind of blower motor combination you're gonna need in order to drive enough air through your HEPA filters. Before we just dive right into the assembly, let's let the professor explain a little bit more about how to carefully calculate the specifications of the blower that you'll need for your flow hood build. All right, let's talk math. As you know, we need to find a blower that's going to be able to create sufficient airflow at pressure to push enough air through our HEPA filter to create laminar flow. This is easy to calculate as long as we know the specifications of each of the individual components. The first thing that you need to know is the static resistance of your filter. This is the amount of pressure that's needed to push air through it. If your filter is worth its spit, this will be printed in the product description when you buy it, and it's usually also printed on the label of the filter itself. This is a measurement of pressure, so it's usually listed in pascals or the more anachronistic inches water gauge. The filters we're going to be using in this video are rated at 1-inch water gauge, which is about 250 pascals. Now, if you're going to be using pre-filters, which I highly recommend, then you're also going to need to know their static resistance and add them all together. In this case, we're using MERV 13 pre-filters with a static resistance of about 0.25 inches water gauge, so our grand total is about 1.25. Next, we need to calculate the total amount of airflow that we want our flow hood to generate. To do this, we're going to multiply our desired velocity by the surface area of the filter. A good maximum working velocity for a laminar flow hood is about 100 feet per minute. Since we're going to be using a 2-foot by 4-foot HEPA filter, that has a surface area of about 8 square feet. So, multiply them together, and we need to generate about 800 cubic feet per minute of airflow through our filter at pressure. Most blowers will have a product specification sheet that will have a graph or a chart that will allow you to see what kind of airflow it can generate at what static pressure. In this case, we need to find a pretty powerful blower that can deliver 800 CFM at 1.25 inches water gauge. It's important to mention here that the static resistance of your filter will actually change with time. As more and more particles get impacted into the back of the filter media, it gets harder for air to pass and the resistance increases. The rated resistance listed on the product specification is usually, in my experience, significantly higher than the resistance that you'll have with that filter when you throw it in brand new. In general, I err on the side of caution. I'll get an overpowered blower and never in all of its lifetime actually ever use it at full power. Chances are, if you're in the ballpark, it's probably going to work fine. At the same time, if you're not thoughtful about it, if you get a blower that's not actually rated for pressure applications, or if it's just simply not up to spec, then it will fail to generate true laminar flow, and your flow hood might not work the way that you need it to. Okay, by now hopefully you've got a good idea about your filter and your blower. It's important to get these before starting the build since you'll need to size everything accordingly. Next up, let's build a box.
For this project, I'm going to use 3/4 inch plywood. It's nice and sturdy, and I'll be joining the pieces by simply screwing into the end grain of the plywood. In theory, cheaper stuff like OSB or even a cardboard box could work for this, but it might require you to get creative to make sure that it's actually structurally sound. I'm going to use pre-finished maple plywood, which means I won't need to stain or seal it, which saves me a step later on. In lieu of a table saw, a great trick to accurately rip plywood sheets is to use a circular saw with a straight edge. The guide on the saw is usually an exact width, in my case 1.5 inches. So you just add or subtract this amount from your measurement. Then you can mark the line, clamp down your fence, and rip away. Make sure to account for the width of the saw blade when your measured piece is on the saw side of the fence. Oh yeah, and don't forget, safety third. My filter is exactly 4 feet wide, and so is the plywood, so I'm going to take advantage of that for the fewest possible cuts. There are many different ways to build a box. So rather than give you a cut-by-cut tutorial, I've made a free PDF with some different design ideas and construction plans, which you can download from a link in the video description. The main thing is that you need to make the box as high and wide as your filter, maybe even a hair wider so that it can easily slide in the front. And you need to make the box deep enough that the blower can sit comfortably on top. The opening for the blower should leave plenty of room for the filter and for the filter backstop. If you don't have any experience building stuff, I really encourage you to ask a friend or a local craftsperson for some mentorship, as all those pesky little lines on the tape measure have this nasty habit of getting up and wandering around when you're not looking. This can lead to a medical condition known as inchitis, which, when left untreated, can cause the much more severe chuck-it-osis. It's always a shame to waste material, especially when you're on a budget. Most carpenters have a soft spot for a friend in need, particularly when that friend comes prepared with a few beers to grease the wheels. Also, don't worry if your box isn't perfect. As long as the filter fits, you'll be able to make up for little gaps when you seal it with silicone later on. Mistakes bespeak the human hand and create beautiful imperfections. For some, this is the basis of a whole aesthetic philosophy, and is regarded as one of the highest achievements in art. I certainly made a few mistakes on this build, though of course I've hidden them with strategic film editing to project the appearance of total competence.
For the sake of simplicity for this video, and also because I know I'm not going to be moving them, I decided to just build a work surface to mount my flow hoods. I think most people when they're building a flow hood just have a work table, buy a stainless steel table that they can mount it on. But typically I like to build them either on some kind of cart with wheels, or I'll just make one large freestanding unit. So I've made a few different plans that you can check out in the description. But I just wanted to show this to you today. I just used a 2x4 frame, some cheap plywood, and then I finish it with snap-in vinyl flooring, which I found is both the cheapest way to finish a surface in terms of just cost per square foot, and it's a nice, durable, easy to clean surface that'll hold up well over time.
I like to clean up the cut edges with a light sanding. Then I'll measure and mark out my screw holes, taking care to make sure that the screws don't overlap in the corners. Next, I'll pre-drill all my screw holes about 12 inches apart, and then I'll use a countersink bit to make sure that the screw heads sit flush and also don't split the plywood. As I begin to assemble my box, I also want to pre-drill into the end grain of the adjoining board, or else I risk splitting the plies apart and weakening the joint. I take extra care to make sure the first hole is perfectly aligned. Once the first couple of screws are in place, the rest are much easier. If you follow my designs, the back of the box is going to be the same width and height as the filter. So it's a good idea to attach this first before connecting all of the sides. This will help ensure that there's enough space for the filter to slide right in. In this case, since I'm building a double-wide flow hood, I'll have the two halves overlap the central divider. Of course, for simplicity's sake, I could also just build two boxes and then screw them together in the middle. Once your box is assembled, it's time to make the backstop for the filter. It's a good idea to measure the actual width of the filter itself. HEPA filters usually come with a gasket on the front face, which will seal against the wood that holds it in place. I like to add a second gasket on the other side, so that way the filter is sandwiched on both sides between foam rubber seals. I'll use some clamps and scrap wood to make a mock-up, then I'll measure the gap between the boards. There's no need to over-tighten the clamps, just a little compression will make an airtight seal.
That's more like 6 5/8.
Once I have my measurement, I'll mark a line this distance from the front edge of the box all the way around. This way I know that the filter will get squished in just right. Now I'll cut some 1x2s to fit tightly around the inside of the box. Some strips of your scrap plywood would also work well for this. Then I'll pre-drill and countersink all my screw holes and carefully screw the boards down using the marks that I just made. Next, it's time to cut the hole for the blower. I want to carefully measure the blower opening and then mark this out on the center of the box. I'm also going to line the blower up with the marks before I commit with the saw to make sure that it fits snugly, and I'll double check my measurements to make sure I'm not going to run into the back of the box or to the filter backstop when I cut through. I use a wide drill bit to start some holes in the corners, then use a jigsaw to carefully cut out the blower opening. That completes the first half of the box. Since I'm building a double wide, I'll go ahead and build the other side. After that, it's time for sealant. I recommend using a decent silicone sealant, as it remains very flexible after curing, though any old sealant should do. I like to seal the entire enclosure, running a bead along each of the seams, then using my gloved finger to spread it and press it in. I wipe my finger with a paper towel between passes to keep it tidy. I'll seal all the seams and also the back and the corners of the filter stop boards. However, I'm going to try to avoid getting sealant on the front of the filter stop because later on I'm going to be using some weather stripping to make a filter gasket, and the silicone can keep the adhesive from sticking. When you're working with silicone, it's a good idea to also have some mineral spirits around, which you can use to clean up any messes. Next up, it's time to assemble the blower.
All right, we've built our flow hood cabinet. Before I dive into the next part, I want to talk a little bit about speed control. In my first flow hood build, I took some bad advice from people on forums and installed a router speed controller in my flow hood to control the flow rate of the air. The thing that I didn't understand at the time is that these speed controllers, much like light switch dimmers, actually use a very simple technology called a triac, which is basically just fluttering between the on and off positions really rapidly. So it's reducing the amount of power that your motor is receiving, and that reduces the amount of airflow. The trouble with using a triac to control the speed and power of your split capacitor motor is that it's putting more undue wear on the motor coils. The result is you'll burn your motor up many, many times faster than you would if you use the method that I'm about to describe. A properly installed squirrel cage blower and motor combination will last for many, many years, and you should never have to replace it. As you've no doubt noticed, there's an intimidating number of wires coming out of the back of this motor. Now, I'll show you, it's actually very easy to sort all of these out, and almost always you're gonna find all of the information you need right here on the motor label. But the reason that this motor has so many wires is it actually has, I believe this is a 4-speed, it actually has a number of independent coils. Because when you install them in, say, an HVAC system in a house, there's a good chance that you might want to have a higher flow rate for, say, your heating than for your cooling or vice versa. So you can wire those systems in to separate coils. What this means is that this motor can run at 1/4, 1/2, 3/4, or full power, giving you a fair amount of control. In my experience, this is more than enough control to dial in exactly where you want for your particular laminar flow application. As I've described previously, I like to oversize my blower so that on rare occasions I could crank it all the way up to the highest setting and blow off any dust that might have settled, for example, if I haven't used it in a while. So instead of using a speed controller that's going to burn up your motor in no time, I recommend using a rotary cam switch. I think this cost me about $10, maybe $20. And because this is a 4-speed motor, I've got a 4-position cam switch. You can also get 3-position cam switches. The beautiful thing about this is it will allow me to wire in each of those coils on a separate position on the rotary switch. So I can just turn it to whatever power level I want and get those coils powered on my motor for higher or lower airflow. Now, if you really want to geek out, there is a way to have continuous speed control on a permanent split capacitor motor, and that's using a variable frequency device, or a VFD. That's because the speed, the ambient RPM of this motor is actually determined by the frequency of the power going into it. And the amount of air that it's pushing at higher or lower rates really has to do with how much resistance there is and how much slower than the max RPM this motor is running in order to push that resistance. But while VFDs are cool as hell, they're very expensive and there's really no reason to install one for this application. Let's move on to assembling our blower. First, we'll want to install the motor into the housing, mount the capacitor, and then I'm going to talk about how to wire this in to our cam switch. We're also going to want to plug our flow hoods into the wall. So for this, we want to get an extension cord. Now, it's really important to buy an extension cord with an adequately oversized wire gauge. It's really easy to undersize the wire gauge. Not only is that going to severely damage your motor by starving it of the necessary voltage, it's also extremely dangerous as the wire could melt, overheat, start a fire, and lead to death,
destruction, mayhem, and chaos.
Now, in order to determine our wire size, we'll need to first look at the amperage draw of our motors, which will be listed right on the label. In this case, it's going to draw a full 7.1 amps, presumably at full power. Now, as you know, I'm going to be building a double-wide flow hood with 2 blowers and 2 motors, which means that I need a wire that can accommodate up to double that amount, or 14.2 amps. This is a 14-gauge extension cord, which is good for up to 15 amps under less than 50 feet. I've got a 12-foot extension cord here. When in doubt, always oversize your wiring. Safety third. Another quick tip, just to save yourself some neck craning and headaches, take a picture of your blower label before you install it, because you're going to need to reference that wiring diagram later. For this next part, we'll need a few tools. Hopefully your blower came with all the parts that you need, but you'll probably want a socket set, maybe an impact driver to put that together. We're also going to be doing a little bit of electrical work. Now, these cam switches usually come with some of these little prong adapters, and these are just crimp-on connectors, which you can just crimp to the ends of your wires. However, I really prefer to solder everything just for peace of mind. For that, I use cheap soldering iron, some heat shrink, a heat gun, and some rosin core lead-free solder. Now you can see here on one side of the squirrel cage, we've got a set screw for the motor shaft. So we want to mount the motor on the opposite side. If you need to, especially if you're using a second-hand blower, you can actually remove the squirrel cage housing by taking out these screws and taking out this piece on the underside. Your blower should come with a handful of things. These motor mounts, as well as the arms to mount them to the motor. And in my case, my blower also comes with these mounting brackets, which in the past I've just mounted them directly to the plywood, but today I think I'm going to try installing these. Now, as you can see, the motor has these rubber collars on the ends, and that's what we're actually going to be clamping it with. But in this case, my blower mounts are actually oversized for that. Luckily, my motor came with the correct size that I need, so I just have to switch those out.
To determine the correct position of the mounting arms, I'll just go ahead and set the whole motor in place.
Now, maybe some of you are some HVAC pros who are going to rag on me in the comments for this, but whenever I install these blowers, I like to mount them a little bit closer on the inside, and these bolts sometimes will end up rubbing against the squirrel cage, so I usually just break them off.
Make sure that the impeller is carefully centered in the housing before tightening the set screw on the motor shaft.
It's worth mentioning here that you've got to be pretty careful with these fins. You'll notice here there's a counterweight crimped onto one of them. They're carefully balanced, so if you damage them, dent them, or if one of them breaks, something like that, it'll really screw up the whole balance of the wheel, and it'll actually cause a lot of vibration and wear out a lot faster.
Next, I'll mount the capacitor to the housing with some pipe strap and some self-tapping sheet metal screws. I want to make sure the screws don't interfere with the impeller movement. Double check by consulting your wiring diagram, but usually the capacitor wires coming out of the motor are brown. One solid and one has a white stripe. They can be pressed onto the capacitor terminals in either order. Now it's time to deal with these other wires. The common or neutral wire is usually white, and this is going to get connected directly to the extension cord that we'll be plugging into the wall. Ground is usually green, and the rest of the wires power the different motor coils. We'll connect the positive wire from our extension cord to the cam switch and then use this to apply power to each of the coils independently. It's worth noting here that if you apply power to more than one motor coil simultaneously, you'll short them out and burn up your motor. Since I'll be using solder and heat shrink, the First thing I like to do is remove the cheap plastic collars from the connectors that came with my cam switch. I'll trim the wire for a clean end and strip just enough insulation off to fit the connector sleeve. Then I'll crimp the connector in place with some pliers or a crimping tool. A solid crimp is usually good enough, but I like to play it safe and solder everything into place. This way, I can trust that the connection is going to hold up well for the life of the blower, through many years of lots of vibration. I'll slip a bit of heat shrink over the wire before soldering the connector in place. Then I'll repeat this process for all the wires, and shrink the heat shrink using my heat gun for a nice finished look. Now I'll strip the ends of the extension cord to get it ready to attach. I recommend soldering this as well, although you can use some wire nuts if you're solder shy. I want to solder the white wire from the motor to the neutral wire on the extension cord. In this case, since I have two blowers, I'll also solder in a third wire that will go to the white wire on the second motor. When I did this, I forgot to slide it through the heat shrink, so I'm going to have to resort to electrical tape on this one. The other end of the extension cord, the hot side, also gets an additional wire for the second blower. Plus, I'll solder on a fork connector to connect it to the cam switch. The cam switch is a modular unit, with each switch in the series requiring its own power input. Most of these switches should come with a bridge connector that will jump all of the input power terminals, since they all share a power source. But mine was either missing or I misplaced it, so I just soldered a new one. I always like to use a multimeter and do a continuity test to make sure that I have the correct understanding of which terminals connect to which in my cam switch. In this case, all of the odd-numbered terminals will share the input power from the extension cord, and the even-numbered terminals will connect to the motor coils in ascending order of speed. This is where that motor wire color chart we took a picture of will come in handy. Now, before I just dive into mounting the blowers, I want to talk about building a top box. Maybe this belonged in an earlier part of the video, and it's really only necessary if you're using pre-filters. But, since you're going to take my advice, and you want to use pre-filters, you'll want to see how this part works. I measure 3 pieces for each box: a front, a back, and the top. These boxes should be wide, deep, and tall enough to comfortably fit the whole blower, ideally with a good amount of space on either side of the blower between that and the filters. I screw these panels together just like I did for the big box, and I'm going to go ahead and seal them with silicone also. Just like that bigger box, I'll install a filter backstop on each side, just about 1 inch from the edge. Then I'm also going to add an extra piece in the center to help brace the filters so they don't get sucked in by the blowers. Okay, it's time to mount the blowers. As you'll see, I made a mistake. I didn't account for the height of the blowers when the mounting brackets are attached, so my top boxes ended up being too short. Rather than rebuilding the boxes, I just went ahead and removed the brackets and installed the blowers as I have in the past, by inserting them down into the opening and then screwing the blower housing directly into the plywood from below. Now I'll center the top box, ideally leaving a little lip in front for the glass tunnel, and screw it down to the flow hood cabinet using several screws through the filter backstop. Next, it's time to mount the cam switch. I'll trace the faceplate of the cam switch directly onto the box, making sure that there's going to be space around it and it won't run into the blower housing or the filter backstop. Then I'll drill out the corners and jigsaw the hole like I did for the blower opening. Now, it would have made more sense to drill this hole before mounting the top box, so I make sure to do this before installing the second one. The cam switch is designed to only accommodate a thinner mounting surface, not a full 3/4 of an inch. So I made my own mounting plate by using an electrical cover plate. Here, you'll see me attach the ground wires directly to the blower housing using a self-tapping sheet metal screw. I'm almost ready to fire it up. But before I do, I want to tidy up these wires a bit using a few zip ties, so they don't get sucked into the impeller. I'll repeat all these steps for the second blower, but this time I'm going to cut a small notch in the back of the top box for the extension cord to go through. Then I'll silicone everything in place for good measure, and finally I can give it a test run, checking that each of the switch positions works as intended. Keep in mind, these blowers are designed to work under load, so they may not move as much air or behave as you expect until you put some resistance in front of them. We're ready to install the filters. First, we need to cut and prep some pieces of wood that we're going to screw into the plywood to sandwich the filter in place. Most HEPA filters have a 3/4 inch flange all the way around, which means that with the 3/4 inch plywood, some standard 1.5 inch wide boards will mount perfectly. In my case, I'll also need a wider piece in the center between the two filters, which I'm going to have to cut on the table saw. Next, I'll measure, drill, and countersink all my screw holes, spacing them about 8 inches apart and about 3/8 of an inch from the outside edge so that the screws will land in the center of the plywood when I screw them on. These boards will be in the path of sterile airflow inside of the tunnel, so I'm going to need to be able to sanitize them before each use of the flow hood. This is why I want to finish them with a high-gloss polyurethane. This step is time-consuming and it's kind of a pain, but it's important and well worth the trouble, since everything you do in front of your flow hood relies on being able to get these boards totally clean. I usually end up doing about 3 coats, allowing each coat to cure completely before sanding it smooth and applying the next one. By the final coat, I'll use some super fine 320 or even 400 grit sandpaper, and I'll thin the polyurethane down a bit so that I can get a totally glassy surface. While you're waiting for the polyurethane to cure, it's time to apply the filter backstop gasket. I take my time with this, making sure to get the corners and seams as tight as possible. For the corners, I'll cut a tiny triangle about halfway through the gasket so that I can keep it from bunching up on the bend. Where 2 cut ends of the gasket meet, I always leave a little extra on both sides so that I can kind of squish them together and get a tight seal. At last, we finally get to install the filter. The filter media is fairly delicate, and you want to keep it as clean as possible, so take great care as you're handling it. This is a really good time to enlist an extra helping hand. I encourage you to take your time here, go slow, take deep breaths. Hopefully the filter goes in without too much negotiating. However, if you're struggling to get it started, one trick is to remove a few screws from the top of the box. The silicone sealant in the corners should be able to flex plenty if the filter pushes the top up a bit. Once it's in place, you can reinsert the screws and get it all snug. I'll walk the filter back a little at a time until it's snugly in place. I make sure to only press on the metal frame, never on the filter itself. With a filter like this one, those thin aluminum separators between the pleats are very easy to bend and crumple. Next, I'll clean up the polyurethane boards, line them up, and gently pre-drill into the plywood. I use an undersized bit so the screw threads have plenty to bite into. Depending on how tightly the filter fits, sometimes it helps to attach the boards first, then tighten the screws a little at a time, working my way around. I also like to have the shop vac handy for this, and I'll hold it right next to the drill to catch the sawdust before it falls into the filter media. Here you can see I miscalculated and ran into a corner screw, and had to switch to a shorter one. With the filter in place, you're officially ready to use your flow hood. Many mushroom cultivators use their flow hoods just like this, which leaves lots of room for moving bags in and out of the sterile workspace. But, as I've said, I think it's well worth the extra trouble to build a raised work surface and install a glass tunnel to increase the efficacy of the laminar flow and significantly extend the functional working area. For this, I'll start by attaching another piece of 3/4 inch plywood in front of the filter. Since I'm going to attach it directly to the table, I'm also going to go ahead and put a screw into each corner of the flow hood from below so it doesn't shift around. Next, I'll install the glass, cleaning it thoroughly as I go. This is 1/4-inch tempered glass, which I ordered from my local glass shop, who had it cut, edge sanded, tempered, and ready for pickup in about a week. It wasn't exactly cheap, though I think it was worth every penny. I would say it's best for the work surface to be made of either tempered glass or stainless steel. The tunnel could be made with untempered glass, acrylic, or really any easily cleaned material, though I still think tempered glass is my top choice. I'm making the work surface 24 inches deep, and the tunnel pieces are 20 inches wide, with a 1-inch overlap of the flow hood box, which makes the tunnel 19 inches deep. I measured the dimensions with extra care, accounting for the width of the plywood sidewalls, the height of the raised work surface, a bit of overlap for the top and sides to rest against the flow hood box, and for the width of the glass on each side, so the top piece of the tunnel is supported by the glass sides. All of the glass is going to get sealed into place, but I also make sure to secure the tunnel using some aluminum flooring transition strips. It's not a bad idea to ask for a hand with this, especially when installing such a large piece of glass. I was delighted to also find some other aluminum flooring transitions that have a perfect channel for the 1/4-inch glass. I used this to make a frame that holds the outer edges of the tunnel in place without disrupting the appearance or the laminar flow. I cut it carefully using an angle grinder and then siliconed it in place. The last step is to seal the whole work area with silicone. Clear silicone would probably look cleaner, but I went for white because I wanted to be able to see and make sure that I got it everywhere I wanted to. I run a bead along every seam and corner, wiping it into place with my finger and cleaning up any mistakes with a paper towel and some mineral spirits as I go. I also seal the edge of the work surface with silicone and some more aluminum flooring transition to ensure that liquids don't seep between the wood and the glass, which has been a problem for me in the past.
Well, there you are, folks. A true top-of-the-line professional-grade laminar flow hood for a fraction of the cost. If you were to try and buy something like this manufactured, it would cost you thousands of dollars. Of course, there are lots of people out there selling flow hoods these days, and a lot of cheaper options. But in my opinion, nothing can beat the satisfaction and the peace of mind of doing it yourself. Not only can you save a heap of money, but you'll end up with something far more lasting and robust. Plus, it'll help deepen your understanding and appreciation of the craft. This has been a long video, and I applaud you for making it this far. Before I go, I just want to say a few more things about maintenance, filter replacement, and repair. But before I do, allow me to say a few words. I wanted to make this video because I really wish that it existed when I was trying to figure all this stuff out for myself for the first time. Perhaps there aren't too many folks who are going to wade this deep, but I think a homemade flow hood is an important part of the mushroom cultivation revolution. And I'm committed to providing the clearest, most accessible information that I can to help as many people as possible join the cause. My name is Paul Lynn, and I'm here to help foster a global community of technologically empowered, ecologically inclined, self-appointed scientists devoted to discovering new and important ways that fungi can help us build more resilient communities, ecologies, and economies. I believe that free education is key to a sustainable future, and that it is devoted service and not profit which is the highest measure of success. If you value my efforts, I hope that you'll consider helping to support the creation of more free educational videos by going to visit my donation-based shop at fungaia.life, where you'll find grain, substrate, liquid cultures, grow kits, and lots more. And by visiting our sponsors and our dear friends over at True Blue Genetics for some of the finest liquid culture on the market. They have a huge and ever-rotating selection of proven, isolated, mushroom-producing genetics, exceptional quality, kind customer service, and great prices, especially when you use the coupon code FUNGAIA to get yourself an extra 20% off and to let them know that we sent you. At last, you're ready to use your new flow hood. Now, I made a whole video on the ins and outs of sterile culture technique called Mycology Lab 101. So I'm not going to go into detail about how to use this here, but there are a few things I definitely want to mention before I go. Each time I use a flow hood, I always turn it on and let it run for at least 30 minutes or an hour to blow off any dust that might have settled and also to clean the air in the room. I also make sure to thoroughly sanitize the entire work area with isopropyl alcohol, wiping the work surface, the filter frame, the underside of the tunnel, and anything else that I'm going to place into the space. However, I am careful to avoid spraying any alcohol on the filter itself, as this will degrade the media over time. Also, I should have mentioned earlier that some HEPA filters come with a metal face guard. I personally prefer not to have one, though this does mean that I have to be extra careful not to damage the front face of the filter. If your filter does have a face guard, just think of it as part of the filter. I recommend not trying to clean it or wipe it with alcohol unless you really have to, or you risk getting stuff clogged on the crevices. Before using a new filter, and periodically throughout its life, I like to proof my flow hood, testing it to make sure that no spores are getting through. To do this, I'll pour a stack of petri dishes, let them cool, and then spread them evenly across the whole work area and leave them open for about 30 minutes or so before closing them, sealing them, and incubating to see if anything grows. I'll keep an eye on the plates for about 2 weeks to a month to make sure that nothing grows and give myself total peace of mind that my flow hood is clean and functioning as intended. As I've said, a well-made flow hood should require very little maintenance and serve you well for many, many years. There are two main things that you can do to make sure it stays tip-top. The first and most important is to change your pre-filters regularly. I use my flow hoods almost daily, so I change my filters every 4 to 6 weeks. For most folks, 3 to 4 months is probably fine, and you can really tell when it starts to get dirty. The other thing is that it's a really good idea to tape off your flow hood if you know you're not going to be using it for a while. This will keep any dust or debris from settling in the filter during storage. You can cut a piece of plastic sheeting or even just use a large heavy-duty trash bag, and I recommend taping it off with blue painter's tape so it's easy to remove later when you're ready to use it again. Overall, the only real downfall of a flow hood is if the filter gets punctured or soiled with something that compromises its sterility. If you accidentally poke a hole in your filter, don't panic, at least not right away. You can easily, quickly, and effectively patch holes in the filter media by delicately applying a bead of silicone sealant and spreading it around over the hole. Allow the sealant to cure, and then make sure you were successful using the Petri dish method I just mentioned. The manufacturer also recommends that you hang on to your old filters, and you can actually cut up the old media and use some Elmer's glue to carefully glue it over the hole if you want to maintain the appearance. Of course, if the filter is too badly damaged, you're simply going to have to replace it. I always try to make sure to have a spare on hand in case of emergency, so if the unthinkable happens, at least I can get back up and running quickly. Obviously, replacing a HEPA filter is not a ton of fun, especially after you've sealed it all in like this. But hopefully you'll only need to do this once every 3 to 5 years. If you've sealed everything in like this, you're gonna first need to use a box cutter to cut the sealant. Then you can just run the steps backwards to remove the tunnel hardware, take off the glass, unscrew the work surface, and then you can unscrew the filter frame, slide the HEPA filter out, walk in the fresh one, and reassemble it just like you did the first time. Before you reassemble it, you can remove most of the old sealant from the glass using a paint scraper razor. But don't bend over backwards for this step because you're just going to apply more sealant over the top. Well, that's it, folks. Thanks for watching. Catch you on the next one. May the spores be with you.
Poop.